Good morning, everyone. We'll start class in 1 to 2 minutes time. Good morning, everyone, and today's lecture is going to be on the topic of digital filters, which we're going to be covering for the next 2 weeks in this course. And in particular, since we're starting on the topic of digital filters, we're going to be looking at how can we use our difference equation in discrete time, as well as the Z transform equivalent of these difference equations in order to formulate and design digital filters in particular. So what we want to see in today's lecture is the background theory as to how we go about designing these digital filters, as well as 1 or 2 example questions that are sort of like the questions you do get on your final exam paper. And we'll also see an example walkthrough on how do we go about designing and solving for the digital filter itself. All right. So we know from our signals and systems course is that any transfer function that we're dealing with typically has some sort of frequency response. That frequency response allows us to design filters where we could eliminate unwanted parts of the signal that are either higher in frequency or lower in frequency or within a range of frequencies in particular. So if we're given a Z transfer function here, and we're asked to find the frequency response of this transfer function, we can do it in 1 of 2 ways in particular. So the manual way is if we switch the Z here equal to e to the j omega, and because it's now with j omega, this capital omega here being digital frequency, we can plot for individualized points of digital frequency and obtain what the h of j omega response is going to be on the y-axis here. And as such, we can plot this h of j omega magnitude response versus its digital frequency as of such. And we can get a nice response graph as whatnot. But this is where we're taking a manual approach. Thankfully for us, there are automated approaches where we can just plug in the Z transform equation itself and we can get the same frequency response immediately. And in MATLAB or Octave, the use of this is using the frequency design analysis tool, also known as the FDA tool, which is basically allows you to plug in any Z transfer function that you require, and it will give you the frequency response as desired for each Z transfer function that you put in. So typically, when you're doing some sort of filter design, you need to design the transfer function to match the frequency response or the frequency behavior of your system that you require. We saw this in particular in continuous time systems, where we had the Laplace transform being the design required for us to develop analog filters. But we also saw that the Laplace transform doesn't work well for sample signals or discretized type signals. So that's why we have the Z transform. And as of such, that means the design process for the Z transform when you're making digital filters is going to be a little bit different. So what we're looking at in this lecture and over the course of the next 2 weeks is how do we go about designing these digital filters to match this frequency response or frequency behavior that we require for our digital systems. So remember, any transfer function in particular, it just basically is going to be some sort of model where we can go in between its domain and its equivalent time domain, be it continuous time or discretized time. In our case, this is going to be discretized time. So it's possible for us to remap this equation here from h of z back into h of n Or we can have it in such a difference equation, and we can have it in its open form solution, as we can see here. No, the reason why I'm saying this is the open form solution is that we have a series of delays for h here accordingly. So you have h of n, but now we have h of n minus 1, and then we have delta of n minus 1 accordingly as well for each one of these. We can also remap this from h of n into y of n to get its equivalent response if we wish. So we can have it in terms of h of n mapping straight to h of z, or we can make that such that, remember, h of z here is just going to be y divided by x. So we can remap this into y of n and x of n accordingly as required. So any different equation that you're dealing with here is going to have some sort of typical frequency response that we're going to be required to plot and design your filters for. And to give you an instance where we might use this, let's say we had our original signal here, you know, a nice sinusoid, but somewhere inside there we have a noise spike that actually occurred. We want to see how do we design our digital filter here to eliminate this noise spike that occurred here in particular. So let's watch this initial difference equation here. And the form of this is basically, when we think about it, it just basically averages these three values here, because we have xn, xn of n minus 1 and n minus 2 here, being three values, and then they're going to be multiplied by a third here. So it comes like we're just doing an average of these three values in particular. So this sort of filter design is what we refer to as a moving average filter. And we're going to be applying this filter here to that previous signal we just now saw with the noise spike. So when we actually do apply that signal here, sorry, that filter to the original signal, which is given in blue here, we see here that the noise spike itself gets eliminated or mitigated in some form or fashion because of the filter being applied to the signal. Yes, there is a little bit of shifting that does occur here, but you can just reshift back the signal accordingly to match back to the original signal at its original time points and as such. There's also a little bit of attenuation that does occur, but that's because of the nature of the filter, because it's a moving average filter, so you get a small little bit of attenuation that actually does occur. So a typical question is, we have the filter design here in discretized time, given by our difference equation, but what's going to be the frequency response of this filter? So we need to move this back from its difference equation form into its equivalent z transfer function. That as such, y of z divided by x of z here is just going to be a third, and each one of these delays here is going to be, whereas n is just 1, n minus 1 is z to the negative 1, and n minus 2 is just going to be z to the negative 2. So it's just a direct transfer function realization when you watch it here, because this difference equation form is basically equivalent to the open form solution that we saw in a few lectures back. So we can just eyeball this and just do the z transfer function, sorry, the z transform of this equation accordingly. So to get the spectrum of this, because this is in terms of z, we need to transform this such that it now becomes, instead of y of z and x of z, which is basically h of z, we need to make this from h of z into h of capital omega, where each one of these z's here is just going to be e j omega in particular. This here is basically the same thing like a summation series. So it's equivalent to shortcuts in the summation series by using either the arithmetic progression or geometric progression formulas in particular. I believe in this case it will be the arithmetic progression formula for the sum of a series. So we get into that in a little bit as to how would the frequency response change depending on how many terms do we have in the moving average filter. So in this particular example, when we do plot our magnitude response here, versus our digital frequency omega, we see here that we get our filter response looking like this in particular. At the centralized frequency here, which is going to be our Nyquist frequency that we intend to match, that means the zero crossings here at these points, is going to be space at 2 pi divided by 3. And you're going to ask, I know someone's going to ask, why is it 2 pi divided by 3? But like I said, the reason why it's going to be 2 pi divided by 3 here is because of this particular design. We're going to look at this in particular when we're going to move to n order moving average filter to see how does the frequency response change, as well as how do the zero crossings change as well. Now, this 3-term moving average filter is actually a poor quality low pass filter, because this is what the ideal low pass filter frequency response is actually supposed to be like. It's just supposed to be getting this first part of the signal here and just eliminating the rest of the signal entirely. When in reality, our full low pass filter is just somewhere around here, which it doesn't match close enough to the ideal low pass filter response. So the moving average filter is only good in particular instances, removing noise spikes in a signal at particular times or intervals. And as such, a moving average filter is only very useful for moving high frequency components. So a noise spike is like an instance of a high frequency couplet within the signal itself. There are also other examples of high frequency couplets that may exist in signals. But a moving average filter is like basically a general quick way to remove these high frequency components if you do encounter them in a noisy signal. So when we move to an n-term moving average filter, the equation basically becomes generalized such that h of omega here now becomes 1 divided by n, and in the summation series this is going to be 1 minus e to the negative j n omega, whereas the denominator here will just remain the same as before, which is 1 minus e to the negative j omega as required. Once we go up in terms of n, each zero crossing, which we can see here on the x-axis where these lines touch the x-axis itself, is going to be mapped by capital omega is equal to 2 pi divided by n, where n is the number of terms for the moving average filter. So in this particular case, where n is equal to 6, the zero crossings will actually occur at 2 pi divided by 6, which is basically pi on 3. And the Nyquist frequency is going to be matching such that the response here needs to be symmetric. So we can see that the Nyquist frequency for this filter is going to be somewhere around 3 accordingly on our x-axis for capital omega. So moving average filters are also referred to as smoothing filters as well. So it's such that it's good for initial attempt to remove high frequency information in our signals, especially when the core information of the signal is low frequency in nature. If your core information is high frequency in nature, that means you're going to have to do an entirely different filter design. But we're going to get onto that like in the course of the next 2 weeks as to how do we go about filtering the high frequency components. Sorry, how do we filter out other components and maintain our high frequency information as required. So in designing our moving average filters, we just only need to know where the first zero crossing is going to be. That basically gives us the value for n for our moving average filter design. So an example question that came on the final exam a couple of years ago was basically, we had an n-term moving average filter to design such that the first null, and the first null here refers to the first zero crossing, occurs at 4 kHz. So we're going to have to figure out what the order of the filter is needed, meaning that we need to solve for n here. And then we had to sketch the frequency response of the filter, assuming a sampling frequency of 12 kHz. Question. So does the moving average filter reduce noise on the signal with a distinct type of shape, such as the PPG or ECG of the monitor? Basically, what a moving average filter does in such a case for the PPG or the ECG signal is instead of okay, it will maintain the shape of the signal, yes. And what it basically does is that the high frequency information in those signals tends to be like any sort of spikes in the signal itself. So what it will do when you apply the movement average filter is yes, it will maintain the shape of the signal, but any spikes in the signal, it's going to attempt to reduce that spike. So it mitigates those spikes as a result of the high frequency noise components that are present within the signal. If it's such that there are no spikes in the signal and you apply the moving average filter, it comes like you're just wasting your time because it doesn't eliminate any high frequency information that does not exist in the signal to begin with. So like I said, it's only good if you have high frequency information that's corrupting your signal. Whereas if you just have low frequency information within the entire signal, a moving average filter is just going to be basically worthless. It applied it in the entire signal. So yes, it does maintain the shape. The only thing that it will eliminate from the signal is any particular noise spikes, be it positive or negative in nature. Alright, so this question here is basically we have the first zero crossing frequency, which is going to be 4 kilohertz, the sampling frequency, which is going to be 12 kilohertz, and we're going to have to figure out what's going to be the order of the filter, meaning that we need to figure out what's going to be the value of n here, and then just to sketch the frequency response of the filter. So the first zero crossing is going to be at, as we saw from our previous slides, it's going to be capital omega equal to 2 pi divided by n. But we need to solve for n here in particular. Capital omega here is also equal to common omega multiplied by t. So we can rewrite this such that common omega is equal to 2 pi divided by nt by doing this substitution. We can then rearrange this formula to make n the subject of the formula so we can solve it. And basically, n here, when we do remappings accordingly, is basically equal to the sampling frequency divided by the first null frequency. So we were given the sampling frequency, which is 12 kilohertz, and then the first null frequency here being 4 kilohertz. So n here will resolve to the value of 3. So as such, because now we know n is 3, that means our movement average filter for this design is going to be a third order movement average filter. And when we sketch our filter response, this is actually what it looks like. Remember, the Nyquist frequency to be half that of our sampling frequency. So we see here that for our filter response, the symmetric part is going to be around 6,000 gigahertz accordingly. So the transfer function for this movement average filter is basically going to be 1 divided by n, and then we just put in the average terms here with each one of the delays to match to the n order here in particular. So because we have 1 divided by 3 here, we just need to have 3 terms in x accordingly for this average in filter to move to match accordingly. So that's 1 divided by 3, we'll have x of n plus x of n minus 1 plus x of n minus 2. So that basically is going to be our difference equation. And it's possible us to actually batch this back to the general form of a difference equation that we saw in lecture 14. If we need to draw this as a block diagram, this filter here is basically a feed-forward filter design. So we basically have our first level here, then our second level, and then our third level here, where each one of these delays here are matched accordingly. In exam calculations, you can just write f of s divided by f, where f of s is the sampling frequency and f is the first null or zero crossing frequency. You don't need to do the derivations. So for our filter design here, this one turn going is going to multiply by each one of delay signals there, being x of n minus 1, x of n minus 2. So this 1/3 here for each one of these triangular blocks is going to be mapped onto these triangular blocks here. And remember, this here is going to be like basically our x of n, which is basically 1. X of n minus 1, which is basically matching to z to the negative 1. And then our x of n minus 2, which is backed into z to the minus 2 here accordingly. And for this filter design, it's a feed-forward system. So this feed-forward system filter design is also referred to as a finite impulse response filter, or FIR filter. And the reason why it's feed-forward, if you watch the nature of the equation, everything was just adding and everything was in terms of x on the right-hand side. So there was no feedback to the output, being y of n here. All right. That brings us to the end of our lecture for today with digital filters. And in particular, what we saw is how did we go about designing for our moving average filter, as well as the importance of why would we use a moving average filter to filter out high frequency components in a noisy signal in particular. So are there any particular questions regarding the material of this lecture for today? Alright, doesn't seem like we have any questions. So if there are any questions, feel free to leave them in the comments down below. You guys can directly email me accordingly as of such. So before I leave, your midterm marks should be released by Wednesday or Thursday of this week. Because they're basically finished at this point with the marking, and it's just to do one or two little quality checks to make sure that the marks are finalized as required. I think I also uploaded problem set 3, but we won't be doing that this week. We'll be doing that next week, Wednesday in particular, because I didn't put up the choice questions as yet on my end. Alright, so on Wednesday's lecture, we're going to be doing our digital filter 2 lecture, which is going to expand on the design of finite impulse response filters, or FIR filters. And then we'll also be looking at how do we do FIR filter design examples in particular after that digital filter lecture on Wednesday. Alright, so until Wednesday, take care, be safe, and I will see you guys soon. Later.